attempt at doing this portion, this video portion. I did such a horrible job before. Okay, so here's the voltage. So let's crank it up to the. Let's show the battery. Let's crank it up to the desired voltage. Now, what's going to happen is these alkalis in here are going to go grab electrons and put them on terminals, or the electrons are going to come in. What the electrons are going to do is they're going to come into the positive side, and these guys are going to grab them and move them over to the negative side. I think that's what happens. Yeah. So there we go. The electrons come into the positive side. These guys go grab them and put them on the negative side. And if we put a wire there, then these guys would take off. All right. So if I want a little more voltage, they'll go grab some more. Stick them over there. So let's go back to 0 again. So let's go to the other side. So here they go. They're going and grab it. The electrons come in from the wire over here, and they go and put them on the negative node so that they can shoot around and do the wire. Okay. And what we wind up with is we got more negative charge over here than we do over here. So I've got a positive and negative node. All right. Which is that's the way it works. All right. So now let's take a look at capacitance. Okay, there we go. All right, so here we go. Q, which is the amount of charge that's on here. Notice we get this little guy up here. It's kind of that we worry about this a lot in way higher level physics, but here we're just worried about what's going on in the middle here. Remember, these two plates are close enough to each other so that it's a uniform electric field going through there. All right, they're plugged in the positive node and the negative node here. And eventually what happens is in the circuit, the electrons come around here and they build up, and these electrons go running over here. Eventually, though, once this equals 12 volts and this is 12 volts, this is going to push the charge this way, and this is pushing the charge that way, and they eventually equal each other, and nothing flows anymore. Okay? And so you've got it all charged up. And so you unplug your phone from the wall, and you go, okay, and then this circuit kind of goes away, and you've got this capacitor that now you can key your handset and stuff like that. You can send text to friends and various things. All right, so Q is equal to C times V, all right, or C is equal to Q over V. Now the next slide looks screwy, and I totally botched it earlier when I was trying to show you what capacitance is. So here's capacitance. Capacitance, by the way, is in farads. Okay, capacitance is in farads. All right, don't forget that voltage is equal to the electric field times the distance. Okay, all right, electric field times the distance. All right, so the voltage, like between two parallel plates, would be the E field times the total distance that it is. But we also learned earlier that Q is equal to echo naught times EA. Remember that when I said you got that line in, when you got an area on a parallel plate, it eventually comes out to be this. EA is equal to Q over echo naught, that permittivity of free space. Okay, so I'm going to take this guy for Q, put it in here, put this guy, and take this guy for V. All right, so here's what we're going to do. We're going to do echo naught E times A is equal to C times ED. Oh, yay. Something cancel here? Yes, the electric field goes away, and then we get the capacitance is equal to echo naught times the area of the plate divided by D. Now, that's a funny looking thing, isn't it? This is where you get the farads per meter, or farad meters. Okay? I can't remember what they said the permittivity of free space is, the units. So let's take a look. Is Coulomb squared per Newton meter squared. Now that's funny. You got a Newton. That's a mass times acceleration. So mass kilogram is still buried in our work. That's amazing to me. All right. So there you go. That's a nice straightforward way of capacitance. All right. 1 over the capacitance is the slope between the charge and the voltage. The energy stored in the capacitor is the area under this curve. Okay, so you get 1/2 QV. So you might be going, wait a minute. You told me, okay, got a single charge, which is what we were doing before. Single charge and a voltage. Single charge and a voltage. Well, the energy is equal to Q times the change in voltage, or the potential difference, QV. Now I'm telling you, capacitor, why is U now 1/2 of QV? Because it charges up. It builds up. The energy doesn't, this is instantaneous. This builds up. And okay. Capacitor has a bunch of charge. All right. You with me? Cool. All right. Now, I don't really look at dielectrics too much, but I'm going to real quick right here. What we do is this is kind of counterintuitive. When we put a dielectric inside, is another word for an insulator. A dielectric inside a capacitor increases the capacitor's energy storage by an amount characterized by the dielectric constant K. It's really kind of cool. In a vacuum or air, so if you put a thin piece of paper between the positive and negative nodes of a capacitor, you increase its capacitance by 3.7 times. These guys, strontium titanate, this is what we use in computers and stuff like that. 233 times you get that thing stored up. All right. Now I'm going to show you one last thing. If I've got it here, I better not have lost it. Now I'm mad because I can't find it. Usually I find it right away. It's always in my way, and I go, oh yeah, I got to show the kids. Here's one of my. All right, I'm going to show you something, and then we'll go to. All right, so here I have a capacitor. Okay, here's my boost cap capacitor, 3,000 farads. 3,000 farads. We're going to be doing farads. This is from one of our labs. We're going to be doing do not reverse polarity. It says 3,000 farads, but very, very low voltage. It works at a very, very low voltage. So you can put a buttload of charge in here, but it's very low voltage, so it won't blow up the building. Basically, if it released all of its energy at one time, 3,000 farads. But notice this doesn't look like a parallel plate. No. Capacitance depends on the geometry of the thing, so that you can spiral a bunch of stuff in here, a bunch of positive and negative plates, get a huge amount of capacitance in it. The material that it's made of, so it's the geometry, the material, all of the above. When you get that conceptual question on your exam on which ones make up capacitor, how do we build a capacitor, and they'll say, oh, all the above of everything that it tells you. Okay? All right, out here on this one, this is tape 2.